Welcome, my dear learners. My name is Sarath Kumar T. I am working as an assistant professor in Department of Civil Engineering, GCA Dharwad. In this video lecture, we are going to see about bending of curved beams. It is the very important topic in Strength of Materials 2, 5th unit. I have attached my mail ID here. If you have any queries or doubt, please email it to this email ID. So, what is curved beam? As the definition goes, a beam in which the neutral axis in the unloaded condition is curved instead of straight, or if the beam is originally curved before applying the bending moment, are termed as curved beams. Till now you have seen straight beams. You know how to calculate bending stresses for straight beams. You know the very popular bending moment equation, m by I equal to f by y equal to e by r. This is advanced topic. So here we are looking into curved beams, not straight beams. We will see what is curved beam, what are the real-time problems, real-time examples of curved beams, how it is vary from straight beams, how to calculate the bending stresses in the curved beams. Finally, we will be able to solve two problems in curved beams. So as you can see, this type of structure you will be seen in a lot of construction sites and also in industries. You have a crane. Out of that, the weight is lifted using a hook. This is called a hook. The hook is one of the main examples, one of the popular examples of bending members. So, curved beams, you can see curved beams in clampers, crane hooks, as I told, frames of presses, chains, links, rings, etc. So, basically, whatever the thing is circular or bent, which is resisting load, you can call it as curved beams. So, how do you calculate bending stresses in the curved beams? How do you design curved beams? How it is different from straight beams? We will see this. So, this is the difference between straight beams and curved beams. In straight beams, as we all know, neutral axis of the cross section passes through the centroid of the section. For example, if you take a rectangular cross section, the central axis will be at the midsection of the rectangular portion. Whereas if you apply bending moment or you apply vertical load, the flexural member, the neutral axis will be lying in the centroidal of the axis. That's how we solve all the problems in the earlier semesters. Whereas in curved beams, one of the main differences is the neutral axis does not coincide with the centroid of the cross section. Okay. Now I am explaining what is the difference between straight beam and curved beam. Later I will explain why the neutral axis does not coincide with the centroid of the cross section. Later I will explain why the neutral axis does not coincide with the centroid of the cross section. Okay. The second difference is the variation of bending stress is linear. As given in the equation below, if you want bending stress here, the equation will be coming like m by I into y. In that equation, m is also in constant, I is also in constant. The only varying parameter is y. Y is nothing but the point where you need bending moment from the neutral axis. The distance between neutral axis and to the point where you need a bending stress. So, the only varying parameter is y. So, the bending stress in case of straight beam will be linear. Whereas in curved beams, it will not be linear. In fact, it will be hyperbolic. So, why it is hyperbolic? We will derive bending stress equation in the curved beams and we will see why the distribution of stress is not linear. Why it is hyperbolic. Similarly, we know the bending moment equation for straight beams is m by I equal to f by y equal to e by r. So, for curved beams, what is that equation? What is the equation to calculate bending stress in a curved beam? So, we will see that. So, here in brief, in straight beams, the neutral axis coincides with the centroid of the cross section, whereas the curved beams, it doesn't coincide. Secondly, the variation of bending stress is linear in straight beams, whereas in curved beams, it is non-linear, hyperbolic. Finally, we know the bending moment equation for straight beams. So, what is the equation for curved beams to calculate bending stresses? These are the things we will be seeing in this video lecture. So before going to any derivation, we are going to derive the bending moment equation for curved beams. This equation is popularly called as Winkler-Bach formula. Before going into any derivation, we have to idealize the structure. Here the assumption goes like the beam is subjected to pure bending. The material of the beam is isotropic, homogeneous, and obeys Hooke's law. Plane sections perpendicular to the axis of the beam remains plane even after bending. Even though it is a curved section, if you cut any point in the curved beam, it still remains plane even before applying loading and after applying loading. That's what it's mentioned here. And as far as strength of material goes, the stress we are applying does not exceed elastic limit. Similarly, each layer will expand or contract independent of the layer above or below it, and also for any type of material used in curved beam, the Young's modulus is same in both compression and tension. These are the basic assumptions we are assuming before going into derivation. So let's see the derivation for bending stress in curved beams. So it is a cantilever beam. ABCD is a cantilever beam, and GH here it is centroidal axis. Here we are considering a layer EF at a distance y from centroidal axis. As you can see, even before applying moment, here we are applying moment. Even before applying moment, the beam is curved. As you can see from ABCD, it is curved. Once the beam is curved, it will have a definite radius of curvature. It is mentioned as R. And the angle subscribed from BC to center of circle, center of radius, center of curvature is theta. Okay. So ABCD is an initial portion where GH is centroidal axis, and EF is a layer at a distance y from the centroidal axis. So once you apply the moment, the beam bends. Since A, B are fixed end or fixed, even after applying moment, the end will be same. That layers will be, the ended portion will be same. Only CD will be deforming. So after that, after applying moment, after it undergoes deformation, the structure will look like, the beam will look like A, D dash, A, B, C dash, D dash, and GH central axis will be changed into GH dash, and the layer EF we are considering y distance from central axis will be EF dash. Now the radius of curvature will be changed. That radius of curvature here it's mentioned as R dash. Okay. So before applying the load, the member looks like ABCD, the curved member. After applying the moment, it changes to AB, C dash and D dash. The curvature changes from R to R dash, and the angle subscribed changes from theta to theta dash. Here you have to clearly understand this figure. Then only you can able to understand well the derivation. Okay. We will go into the derivation. And my kind suggestion is don't simply look into this video lecture. Have a note and pen with you. You start doing this derivation with myself so that you can understand clearly. Here we are not before going into the derivation. The derivation looks little complex and little tedious. We are doing nothing. We are calculating what is strain in the layer EF, and after calculating the strain, we are calculating what is the stress. And once the stress is calculated, we know we will calculate force, and finally we will calculate moment. Okay. So strain, you know what is strain? It is change in length by original length. So we will be doing that only. After calculating the strain, how will you calculate stress? Stress is nothing but strain into Young's modulus. So once you calculate stress, how will you calculate force? It is nothing but force into, how will you calculate force? The force is nothing but stress into area. Once you know the force, what is moment? Moment equal to force into radius or perpendicular distance or any distance. So that is moment. So it seems easy, the concept is easy, but the derivation, the mathematical part seems little difficult. Okay. So as I mentioned, R is the radius of curvature of central axis GH. Y, it is a distance of fiber EF from GH, and ABCD dash, after applying moment, the initially curved beam ABCD changes to ABC dash D dash to be the strained portion of the beam. R dash is the change in radius of curvature. Y dash, initially the distance between EF and GH is Y. Now it is the distance between EF dash and GH dash is Y dash. M is the moment you apply. As I told, theta is the angle subtended. It changes from theta to theta D dash, and B is the width of the beam. So GH, the length of the layer GH. We are calculating length of the layer GH. Arc length is nothing but radius into angle subtended. So GH is R into theta. Similarly, we will be calculating EF. So EF is nothing but the radius changes from R to R plus Y. So R plus Y into theta. So here GH is R theta, whereas EF equal to R plus Y into theta. So EF dash, after its deformation, RY dash is R changes to R dash and Y changes to Y dash and theta dash. So now we are calculating strain in the EF layer. So change in length is EF dash minus EF divided by original length. So we are the strain in EF comes like EF dash minus EF divided by original length is EF. So after you substitute the terms we have derived earlier, R dash plus Y dash into theta minus. So if you simplify it, it will be very simple. R plus Y theta, in second term R plus Y theta divided by R plus Y theta becomes 1, and the first term it will be like that. So strain in EF is nothing but R dash plus Y dash into theta dash divided by R plus Y into theta minus 1. So similarly we are calculating strain in neutral axis. Strain in neutral axis. So this is the first strain. Will there be strain in neutral axis? Normally in straight beams there won't be strain in neutral axis. But in the difference I told you, in curved beams the neutral axis does not coincide with the centroidal axis. Only in neutral axis the strain will be 0. Here, since the neutral axis and centroidal axis are not coinciding, there will be strain in centroidal axis. There will be strain in centroidal axis. So similarly, the strain in GH E0 can be calculated as GH dash minus GH divided by GH. We know R dash theta dash minus R theta divided by theta. Similarly, it will be coming like E0. So E0 is the strain in centroidal axis, okay, GH, where E is the strain in EF axis, okay. So here I am changing, with this equation I am going to find theta dash by theta. So I am going to simplify it. I am not doing anything great. I am just simplifying it and obtaining theta dash by theta, R into 1 plus E0 divided by R dash. I am going to substitute this equation in the strain equation of EF layer. So instead of in equation 5.12, instead of theta dash by theta, I am substituting R into 1 plus E0 divided by R dash. The equation will be coming like this, okay. After that I am going to simplify it. Once I simplify it, I can easily derive this equation. E is 1 plus Y dash by R dash divided by 1 plus Y by R into 1 plus E0 minus 1. You have to solve, if you see this lecture, you will not be able to understand what I am telling, but if you simultaneously solve with what I am telling, you will be clearly understand what it's in this. So till now, as I told, first you have to calculate strain. From strain you have to calculate stress. From stress you will be calculating force, and from force you will be calculating moment. So this is the strain equation. So once you got the strain equation, for calculating stress, what will you be doing? So you have to multiply Young's modulus. So Young's modulus times strain is nothing but stress, okay. Before going into that, we are making one more assumption. We are assuming radial strain is 0. So since the radial strain is 0, the Y distance will remain as Y even after deformation. So we have substituted that. After substituting and taking LCM, you will be getting the third equation, and after that adding and subtracting E0 Y by R, you will be getting in the numerator and simplifying. You have to take the equal terms outside and you have to simplify it. You will get the strain term as E0 into E0 plus 1 plus E0 into 1 by R dash minus 1 by R into Y divided by 1 plus Y by R, okay. We will be continuing this derivation in the next lecture. Thank you.